Um, so I think we may start. I'll first introduce Aaron. Hi, everyone. Welcome to the first of ACM SydCHI's monthly talk series. I would like to begin today by acknowledging the Wangal people of the Eora Nation, traditional custodians of the land on which we meet today, and pay my respects to their elders, past and present. And I extend that respect to Aboriginal and Torres Islander peoples here today. I'm Baki Kocaballı. I'm a lecturer at UT School of Computer Science and the treasurer of the ACM SydCHI local chapter. Today, I'm very pleased to introduce our speaker, Professor Aaron Quigley. He's the head of school for UNSW School of Computer Science and Engineering and the technical program chair of ACM EICS 2022 conference. He has served as a general chair for the ACM CHI's 2021, a program chair for ACM IUI conference in 2018, a general chair for the ACM Mobile HCI conference 2014, and a general chair for the ACM UIST and ACM ITS conferences in 2013. Professor Quigley is an ACM distinguished member, and his research interests include discrete computing, global HCI, pervasive and ubiquitous computing, and information visualization, on which he has delivered over 50 invited talks. He's a member of ACM SydCHI Steering Committee for the CHI Conference Series and a member of ACM Europe Council Conference Working Group. From 2015 to 20, Aaron served first as the ACM SydCHI Adjunct Chair for Specialized Conferences and then ACM SydCHI Vice President for Conferences. From 2016 to 17, Aaron was a convener for ACM Future of Computing Academy. Aaron's research and development has been supported by the EPSRC, AHRC, JISC, SFC, NDRC, EU FP7 and 6, SFI, Smart Internet CRC, NICTA, Vacuum, IBM, Intel, NVIDIA, Google, and Microsoft. He's published over 180 internationally peer-reviewed publications, including edited volumes, journal papers, book chapters, conference and workshop papers, and holds 3 patents. Please join me in welcoming Professor Aaron Quigley, who is going to talk about human-object interaction today.
Thank you very much for that embarrassing introduction. I need to cut down my biography. Okay, so the general background to human-object interaction typically looks at it from the computer vision point of view. Now, a little bit of what I'm going to be talking about today is on computer vision, but it's largely on other techniques that don't necessarily rely on this type of take an image, segment it up, label it, and then try to make relationships between the individual objects that we actually have within the scene. So you can actually see this through, if you go into the literature in CVPR, in CHI, in VRST, and other areas, you'll see a lot of research goes on in terms of segmenting, labeling, template matching, recognizing individual objects maybe that are occluding one another, and then trying to actually build up a scene understanding, and then injecting a human, and then trying to actually understand the relationship between the human and the objects, and then as a result, what activities might be underway. So we can see this in lots of literature, you know, be it at the small scale indoors, be it at the large scale outdoors, between individuals and then the physical objects in the environment around them. So if we actually go into some of the recent sort of deep learning literature, let's say from, again, CDPR, you might see this kind of human attention centric network object human interaction. So if you look at human object interaction, this is the kind of research that you typically see. It's take a computer image, segment it out into the individual objects, and then basically try to build associations between the objects that you've actually recognized. So let's say person one interacting with object one, like a knife, object human two interacting with a cake. And that's the type of human object interaction that's typically built up in the literature. This, of course, has become very, very popular as deep learning has, taken off. This is a very big task that's now actually tackled within the computer vision literature. Again, segmenting it up, breaking it down, identifying it, and then in some cases, maybe passing it through various forms of convolutional neural networks to actually do the identification. So if you look at the literature, the background in this area, you actually see this pre-processing step, selecting areas of interest, precise processing of those selected areas, and then making decisions saying, what are those objects? What are the interactions between those objects? But there's one kind of key assumption that I think we should revisit in all of this, human object interaction, which is this image segmentation. And I would argue one of the points that we need to think about for human computer interaction is what happens when we don't have an image? What happens when we don't have this global camera view? Because I would say this is what we're often looking at in a lot of this literature, this outside in view, where we assume we've got cameras in the environment because of, let's say, CCTV, or we've got cameras built into the home because that's the setup that we've got, or people are carrying cameras with them. So we have this idea that we have this sort of panopticon of cameras that are actually looking in on the human and then actually doing the processing to actually recognizing the objects that are with the human, around the human, and then basically trying to do human object interaction off the back of it. And I would like to say that maybe we need to turn this around, that we need to do an inside out view. So actually, instead of just imagining us being surrounded by cameras and then doing computer vision processing, what do we actually have on and around us? So for example, we might have devices that we're carrying, glasses that we're wearing, smartwatches that we have on our bodies, clothing that we're wearing, shoes. One of my new postdocs that's coming to join us very soon, I hope, fingers crossed, does a lot of work on shoe interaction. So looking at what is on and around us and then using that to project out from us to actually understand what the objects are in the environment. And I'd like to talk about some of the projects that we've done over the last 5 or 6 years in this area, beginning with radar, because this is something I'm continuing to look at, and we actually just got a funded project with a Korean company in this area, so I'll be hiring some new research associates to help out in this area. So if what I'm talking about now is of interest to you, please get in touch, because I'm going to be recruiting somebody in the next few weeks. So this all kind of stemmed from this original work that we did around RadarCat, which was radar-based categorization of objects. We published it in WIST, and we published follow-up on UbiComp, then we published some work in PACM, we did some follow-up work in some other journal that's escaping my name, my mind at the moment. But basically, this is the kind of the root of all evil when it comes to our looking at radar and categorization. Now, the scale we're looking at is not this scale, like not these type of industrial large-scale radar, not this type of use of radar for looking at objects and craft in the sky, or even necessarily looking at Doppler radar for looking at weather patterns. We're looking at a much smaller scale. Now, this was the first device that we actually got access to, but following this, we got access to more types of devices from companies like Infineon. And beyond that, there's now a huge swathe of different radar chip manufacturers that you can actually get access to. The basic idea is that you get these very small miniaturized radars, which typically are what are called monostatic, which means both the receiving and transmitting elements are fabricated onto the same surface together. And these are quite small, with the intention, Google's original intention was to build these into their smartwatches. What we're actually seeing at the moment is Google is releasing this inside of, let's say, Nest home devices or Google at home devices. So you don't actually have to have buttons on the device, but you can actually gesture to the at home device. So the SolI device, the SolI chip that Google originally worked on is showing up in Google products, just not showing up in smartwatches just yet. What we had was this very small kit, and again, we're still using this even to this day, and that's basically the size of the chip that you're actually talking about. It's about the size of a pack of playing cards. Now, when Google originally envisaged this, they were looking at it for doing gesture at a distance, and this is typically what you see now when Google releases products that actually have the SolI built into it. So the Nest has this type of gesture interaction, and the Google at Home device has this type of gesture and interaction to basically allow you to swipe, to grab, to click, to move a slider up and down to control without necessarily having physical buttons on the device and the object that you're actually interacting with. So they did a lot of design, user experience ideation around this to think about buttons, dials, sliders, and trackpads. Way back when we were some of the original groups to have it, there were people publishing all the work that they were doing. And if you look at this video, you can actually see most of the interaction is around at a distance. But what we were using it to do was basically object recognition to recognize different types of materials and objects. And that kind of leads to this type of work, which is, can you actually begin to recognize objects that are in proximity to the radar sensor? Now, that means if the radar sensor is in a phone, you can actually start recognizing objects around it. If it's in a smartwatch, it can start recognizing objects around it. If it's in other household appliances and objects that are there around it, it can actually start recognizing the objects. And that's what we're interested in. Can we passively recognize the objects in the environment without necessarily relying on a camera that would actually want to do this for us? So how does this work? Well, here's just an example of it with water. So the idea would be that you'd be able to use everyday objects then to interact with the computer. And this is kind of why I want to bring this up, especially in the SydCHI chapter here in Sydney, is that I think there's probably quite a lot of people who are actually thinking about interacting with objects using different types of technologies. And I'd like to find out and make connections with other people. This also means you could do body shortcuts, and you could also do automating various processes like sorting waste and quality control. But of course, there's lots of other approaches out there: RFID, barcode, spectroscopy, and these type of things. The point here is that this is untagged. You don't need to change the objects. You're not looking at surface detection only. You can also look inside the objects, and you can also use it for interactive real-time applications. So as I said, there's lots of work, lots of related work out here using light, using EMG sensing, using EM sensing, looking at vibration patterns, looking at weight detection, looking at hybrid approaches with a combination of both vibration and weight detection. Of course, in the radar area, we also have existing work where people have used ground penetrating radar to understand what's below the surface, or even putting radar onto drones to actually understand the physical environment, or even things like terahertz imaging to actually look at the structure inside of objects. So there are, penetrative types of sensing that have actually been used before for doing object detection. But I'm thinking radar sensing is still an underexplored area within human-computer interaction. So you can see here what's actually happening is the 8 channels of data are being emitted. And as the hand is moving, you can actually see there's quite a lot of variance in the return signal characteristic. But when you place an object statically in proximity to the radar or at a distance from the radar, you actually start getting these very defined patterns. And it's those types of patterns that we're actually looking for inside of RadarCat. So what's really going on here is that the energy is being transmitted from the radar and is then being reflected back from the object. But it's not a mirror. If it was a mirror, it would be much easier. What's actually happening is a much more complicated process. Part of the energy is immediately reflected from the first surface, but of course, part of the energy actually gets absorbed into the object and then actually gets reflected back. Some of it here hits the rear surface of the object potentially and then gets reflected back. And some of it just transmits straight through the object. And certain types of objects have great transmissive properties. So a lot of the radar energy actually passes straight through them. So they're effectively invisible. But of course, others are effectively act like mirrors. They absorb almost none of the radar energy and they reflect it all back. But what you end up getting are these types of signals that you're seeing. We're looking at it across the set of radar bins and looking at various amplitudes. And each of those lines basically represents one of the 8 channels. And how we're getting 8 channels? Well, we have 2 transmitters and 4 receivers. And if you multiplex them, you get 8 channels of data that you can actually deal with. So the way we handled this originally, and it's kind of evolved since then, is we basically do this type of machine learning training process where we take the object, we extract the data, we do feature labeling on this. In the original work, we were looking at 661 features, and that's varied depending on the projects we've done since with food and other types of things. Basically, we break up the bins, we look at global maxima minima, absolute value, mean squared type value, so very various features that we actually have. We build a classifier, and then we have our machine learning recognizing process. And then what we do is we can reintroduce the object and we get the same features again, and then we can use, let's say, a random forest classifier to actually do the determination of what we're actually looking at. And once we recognize the object, then we can actually build applications off the back of that. So you're getting lots of raw signal data that you're actually dealing with when you're basically building your classifier. And even things that look quite visually similar, like aluminium and steel, actually have, even to the eye, quite dissimilar characteristics when you're actually looking at their radar return profile. Even things that look very visually similar, like porcelain plates and ceramic plates, actually have different physical characteristics because of the reflective property of what's going on inside the object. And so, as I said, like what you actually end up dealing with is lots of channels of data, lots of extracted features, and then lots of enhanced features that we basically extract. And as a result, we have about 661 features that we're end up dealing with using random forest classification. These are just some examples of the random forest that we actually build. These are just zoomed in on one individual tree within the rounded forest to have a look at what's going on in there. So of course, as you would expect, various features are being used to make determinations as to which path through the tree you do, and then you basically just take all of the trees and make a determination based on what the majority of the trees are actually telling you is the classification that you're looking at. So in the original work, we did a series of experiments with day-to-day objects, plastic materials, and body parts, and I'll just quickly run through those. We did some common household objects that you would find in the office and in a kitchen, and this is the type of confusion matrix that we actually got back. So this was, a repeated study, multiple rounds of data collected twice a day, placing the object on 10 times, evaluating using leave one out with an average accuracy across in this experiment of about 96%. But of course, there were some confusion. There's things like book and wood were being a little bit confused with one another, or even things like aluminium, the external hard disk, or a scale, because they actually have similar component properties within them. And when you get into something like transparent material, like air versus different types of PVC, different types of acrylic with different thicknesses, with different colors, you're actually getting much better results overall. Here you're seeing a little bit of confusion, but largely very high degrees of accuracy being recognized by these types of acrylic. And the reason we did that is the SpecCam paper did a baseline using this type of object recognition. Of course, then the more interesting one for human-computer interaction will be actually also thinking about body parts. So if we have this type of device, can it actually recognize where it is on the body and then use that for new forms of interaction? Again, here we did a study on the different parts of the body. So of course, some parts were covered, some parts were uncovered. Of course, there was some confusion when you're looking at, let's say, the forearm, the belly, and the calf. They get confused with one another. So one of the application scenarios we had was using creating a physical dictionary, where basically you could imagine, let's say for cooking or for shopping. So when we actually had this video released, we got quite a lot of interest from manufacturers who basically build electronic weighing scales for supermarkets. The people who go in and put down the bag of tomatoes, but it's actually a bag of incredibly expensive avocados, that's very difficult to determine when the bag is sealed. But the idea here would be to maybe use something like RadarCat to do that. And we did some trial projects, and there's now some commercial developments underway. Another application we did was using tangible painting, where we were actually using a mouse on top of different surfaces and then using that to select different tools. And you can imagine this being kind of built into a physical palette, so that instead of it being, at this scale with a mouse, it might be something that you would actually have inside of a physical palette, let's say with a pen that was actually doing the determination of what it's actually interacting with. All the way through to the body interaction. And this was we only did some early work on this, but I still think there's quite a lot to be done here, which is basically knowing, is the device in a gloved versus an ungloved hand, and changing the interaction style as a result, or knowing where the device is on the body, so that, let's say, if you put it into a sports cuff versus putting it in your front versus your back pocket versus placing it in proximity to your hand, different types of applications can actually be triggered as a result of this. Okay, and again, this is all using supervised machine learning here, the canonical example of firing up a food application when it's putting on your stomach. I'll jump over this last one, the automatic refill. Lots of applications in here, and some of these have actually, we had commercial interest around, let's say, automatic waste sorting. That's one of the commercial products that we're working on at the moment. And then also things like, self-checkout, and that's one thing that's kind of under development within some manufacturers in the UK and Germany have licensed the IP to actually explore doing exactly that. So if you see that in the future, that's kind of as a result of this RadarCat work that we did back then. Of course, there's various limitations in the original work. It had to be flat, it had to be near, and also we had to kind of rebuild the clutter map from time to time. Some of the follow-on work we did was basically taking this, but to actually look at it from the perspective around counting the objects, so understanding the objects, but also being able to count them. So our contribution there was in this intersection between the two. Now, again, there's lots of related work out here. There's computer vision, there's magnetic sensing, there's capacitive sensing, there's things like RFID, NFC tags that can actually be used. So if you look at the vision-based work, this is similar to what the criticism I had at the beginning around this. You need to have a camera looking in on the physical environment, which you don't always have. If you use capacitive sensing, of course, you actually then have to be in contact to actually maintain a connection between you and the capacitive surface. But you can also use magnetic sensing, but again, that's quite bespoke and specialized. So there's some examples there of other work that's tried this. And you can also think of things like NFC or RFID type of tags. And then, of course, what's interesting is people who've looked at like acoustic paths as a way to determine sensing, or even looking at say just the constraint of like how you're touching the device might actually be a way to determine the object that you're actually interacting with. The important point in all of these is that you're not having a camera looking in on the environment. You're basically piggybacking off of something else to actually determine, to know what type of object are you actually interacting with. And then people, of course, have tried the hybrid approach, let's say putting RFID sensing along with magnetic sensing together. And you've resulted in things like, the Gauss RFID or even the Zanzibar project from Microsoft are good examples of that type of hybrid sensing. And there's lots of limitations in here. I'll jump over these. You have to combine the sensing. It's often quite bespoke. It's not something that you can imagine necessarily to easily deploy. So in this particular study, we were interested in, could we use radar for stacking, ordering, and movement of planar objects? Could we use multi-channel radar for this? And could we understand the permittivity of the object at the beginning to understand how it's reacting to electromagnetic energy before we actually even do the preliminary study? And that was a more specific question that we actually began with. So what we actually first did was we basically determined the power ratio and also the phase difference. Now this was using a microwave network analyzer. So this are basically two plates into which we place a single card. And from that, we actually determined the power ratio and the phase difference. And that shows us that as we put in 1, 2, 3, 4, 5 cards, we should expect to see differences in the power ratio, and we should expect to see differences in the phase difference, just from a physical measurement using this network analyzer, using these two waveguides, basically two plates that are strapped around the cards. That gives us confidence that the return characteristic signals that we should see from SOLI should allow us to tease these things apart. What we then tried to do is looking at free sensing versus token-based sensing, which is basically putting in different types of constraints on top of the sensor, and then putting in different types of tokens on top of the sensor to see if we could actually explore that space as well. And we did different sensing modes: counting, ordering, identification, orientation, movement, and then distance to an object. We did an evaluation similar to what we did with RadarCat, various rounds, various frames, but this time we tried both support vector machines and random forests. With the counting, you can see here, as I'm lifting off the cards one by one, the cards are being counted up. In the second example, you can actually see the hourglass is actually being counted. And as the glass is being filled with sand, that's being measured, not the weight of it, but just the radar reflective characteristic of it. And then likewise with the sheets of paper being counted here. You still see the cards are being counted down each time they're being moved, or with these types of poker chips. We then tried ordering, so we had different types of combinations of cards on the top left, or different combinations of Lego bricks in the top right. So as you're placing them onto the sensor, you can actually see the shape is actually being recognized. In the bottom left, it's actually combinations of coasters are being recognized, or even dominoes were being recognized as well. And you might use it in gaming, for example. So again, lots of evaluation here with the ordering, the coasters, and the Lego bricks, and there's some data sets there that you can actually try. We also tried using it as a new form of interaction with different types of constraint sensing surfaces. I'll jump on here. Again, we did evaluation around the orientation, the movement, and the distance there. Some of the results were without the case, the cards did quite well. Without the case, things like sheets of paper. And what we actually started to discover there is that the paper is not as flat as a card, basically, and the buckling actually starts to interfere. So we actually have to explore new ways of doing that. But even like poker chips work quite well at scale. Here you can see with and without the results, with and without the case, and I'd point you to the paper to have a look at a little bit more detail there. Or even the credit cards with and without the case. What you're actually seeing is the different permutations of the cards are actually being recognized. But with the constraint, with the case, we're actually getting much higher accuracy, up at 99.54%. So we have more, so I'm going to skip over that one. In the paper, there's more details about the actual exploration of that type of sensing. And I still think there's more work to be done. And that's why we're doing this commercial project at the moment. And I'll be hiring somebody in to do some work around this type of sensing. Now, another area that we've looked at is using computer vision, but not using it in a sort of a traditional way. So we've tried to look at it doing local, proximate, and what I would refer to as out of focus vision processing techniques to actually determine the objects that you're actually interacting with. So in this case, we were considering the scenario of somebody using a phone, and they weren't using the phone to look at the screen. They were actually using a phone to basically just hide it because they wanted to keep it in their proximity, but they didn't necessarily want to be having the screen disturbing their social conversations with other people. So this gave us the idea for having SpecCam. And with SpecCam, what you're seeing here is the front source, the front camera, sorry, the front screen is flashing a pattern of light. That pattern of light is bouncing off the table or the object, and then is reflected up to the camera on the phone, which is actually being recognized. Okay. So basically what's happening here is you're doing color and surface material detection. You're just leveraging a pretty simple use of the camera as a multispectral light source, but also using the magnetometer. And then we have different surface materials have different spectral properties. And this allows us to recognize, is it placed on wooden table, sofa, or maybe even, let's say, an aluminum laptop. The inertial sensor is also used, and we also use the magnetometer to determine whether or not it's in proximity to metal or non-metal objects. So there's a sort of there's a fusion. Of course, you know, the challenges are the phone is facing down, so the camera's not going to be focusing. There's going to be no light entering the camera, so you have to deal with that. And there's going to have to be some balance associated with this. So what we did was have this bumper case, and then basically use the bumper case to give us a little bit of a gap. But of course, since we did this work, what we've actually now discovered is new phones are actually coming out with embedded cameras inside of the screen, and there's enough distance between the camera and the surface and the light source to actually replicate this type of study. So this is basically what the camera sees when it's actually placed on different types of objects, and then the light is actually flashed. So you can see that with red objects, you get quite a lot of red reflection, but things like wood, you get very different types of patterns that are actually being reflected back. But similarly with paper, ceramic tiles, polyurethane, polyestyrene, steel, copper, mouse pads, different types of objects, even different things like breadboards and foam. We used a Galaxy S6, so we had a very good light source for this, and to have a look at the reflected light characteristics that were coming back. Interestingly, the AMOLED versus LCD were giving us quite different characteristics coming in. I can't see the chat at the same time as doing the presentation, so if somebody wants to ask a question, I'll have to pause.
Alan was just leaving and saying goodbye.
Okie doke. So we did an evaluation here with color, different types of materials. Ground truth was using a spectrometer. And then we did similar approach to what we did in RadarCat. We printed out, color sheets, but we also used commercial color sheets. We did random positions, and we actually discovered that we got higher accuracy than the spectrometer. And the basic reason for that is we have a larger surface area that we were covering with our light source. The spectrometer is a very small point source of light, but with the screen that we have, it's much larger. So you're actually getting a much larger sampling of the surface. Yeah. And then also we tried out with both our own printed colors, but also with commercially available Pantone cards for experimentation. I'll skip through this because I realize that I'm kind of slightly running out of time. You can have a look at the paper for more evaluation. Very accurate, but there's actually still more work to be done, I think, in this area. One of the points of more work to be done here is actually new forms of phones, new forms of blurry image processing, I think is required. So where we actually have more cameras that we're holding on and around our body. So for example, you might imagine somebody could do this with, let's say, the new Facebook glasses. So as you place the Facebook glasses face down on something, is there enough light that's actually bouncing off the surface that the camera could actually do this processing, so the smart glasses would actually also know where they are, simply based on the fact that there's enough light coming in. It doesn't of course have a multispectral light source to do this, but it could use similar techniques. And so some various potential applications there. And lots of limitations, of course, at this beginning of this work. Another area that I'm kind of still keen to explore more on is looking at touch. So here we were basically trying to understand, like, what are the hands actually interacting with, and how could we actually determine what that might be? So here we're looking at flicking, pushing, and rubbing. And the way we were doing this was by looking at the Jin's Meme EOG sensor glasses. I'm going to turn down the audio here. It's very distracting for me. Do you actually hear the audio from my videos? No, you don't hear the audio from my videos. Okay, that's fine. I'll have to just do a mouse over. Sorry, a voiceover. Okay, I'm going to turn that down.
You should be able to click a button that allows the sound to come through when you share.
Really? Does anybody know how to make the sound come through?
So when you take share screen, on the bottom left-hand side is a button about sharing the audio. The only thing is I think you have to reshare the screen to do it.
Okay. Stop that share.
Aaron, sometimes if you just use the laptop's own speakers, they can be audible.
The problem is I'm using my
take share screen and bottom left-hand corner.
Advanced sharing. I see.
Share the sound of the computer.
Oh, you don't need to take advanced. It's just on the first screen. You don't need to take advanced. Bottom left-hand corner.
I see. Share sound. Perfect. Thank you.
Yeah.
Can you hear that now? Great. Okay, so that's flicking and pushing. So the way this is working is you actually have an EOG sensor in the bridge of the smart glasses that the person's wearing. They're not that smart. Like all the glasses really have is an EOG sensor that's actually built into them. You get a set of signals from what's called a Jins mean glass, the left, right, horizontal, vertical, and you also get this small amount of gyroscopic information. And again, we used a set of features there to determine this. We tried different experiments with people walking, but there's obviously a set of limitations that you would actually have within this one. I'll let the video play so you can actually watch it the full way through. Now, what's interesting, oh, sorry, I just want to play this one. What's interesting, again, with this inside outlook view is that when you have the glasses, of course, the glasses might be on your face, but sometimes the glasses won't be on your face. They might actually just be in proximity to you. So if they're in proximity to you, let's say they're just sitting around you, what else could you actually do? Well, there's enough information from the proximity of the glasses to actually determine gestures that you're actually issuing in the proximity of the glasses to actually detect whether or not you're swiping to the left, to the right, and that's just above the glasses. So when they're on your face, you're getting quite a strong signal, but when it's when they're on the desk, you can actually still repurpose them for doing other types of gestures. Then you have to think about, like, where do the glasses live? Like on your head, on a shirt, in your pocket, on the desk, all around you. Could they actually be a portable sensor that you could also actually use in and around your body for doing types of interaction? And could they actually understand where your hands are and where they're moving around you? Okay, and that was a small paper that was published at SydCHI this year. Another branch of work that we've done, I want to show two, I want to end on another person's talk. It was the Epistener work. Now again, so we, as I said, looking at the inside out view of object recognition, what we've done now is we've explored, radar, and can we actually use radar to look out at the world? We've got the phone, and maybe the phone is being placed in proximity of objects, and that can actually be looking out to the world. As I said, this postdoc who's coming to join me soon is looking at shoes and seeing if they can actually be used to detect the surface that you're walking on or your activity and your exercise. But then you've also got people who are wearing smartwatches. So in this case, we're using the smartwatch to actually look at the back of the hand. Take-home message here was to just basically, can you look at the epistener, which is this region in the back of the hand here, and actually determine what the fingers are actually doing? Now, the basic work was quite simple, okay? It was looking basically for skin deformation, for bone movement, for tendon movement, and for the web of veins, and then using that information to determine what the hand is actually doing, okay? So what you end up getting is something that looks like this. This is the original mock-up version of it, which is just, now what's important here is the camera that's looking into the environment is not seeing the fingers. It's only seeing the back of the hand. Any of the finger information is not there. That's all being inferred from the deformation that you're actually seeing with the hand. Now, again, you can see here that actually allows you to recognize, let's say, different types of tapping. And in this case, you can actually see it's being used to control a gaming application. I realize we're coming up to 38 minutes past, so I want to make sure I jump on to the next video. This is just a simple game. Again, just looking at the deformation of the back of the hand. I want to show you the follow-on work, but actually I'll ask my colleague to present it because and I'm going to have to stop this sharing and share something else so that you can actually see this. Sorry. Because the follow-on work, well, the original work with a pistoner was quite nice. It worked reasonably well, but the follow-on work is much more impressive as a piece of as a piece of research.
Not email from your boss that you have to finish before the big meeting starts.
Skip this one. Okay. So this was presented just late last year, and there's actually also some follow-on work that's underway at the moment on this. See if I can find the right screen to share. So too many things to juggle here. Okay, share screen. Okay, let's have a look. And share the sound, okay. And okay, hopefully you can all see this video from WIST.
Hello everyone, this is Erwin from CMU and Tokyo Tech. Today I'm going to introduce and demonstrate a new hand pose interface for wearable devices. Here I said demonstrate, which means during the presentation I will use the proposed system instead of the mouse to control the slides. As we may know, hand is one of the most natural ways for us to interact with other objects. Therefore, thousands of studies were done to recognize humans' hand pose. However, there is still lacking a very natural way to detect users' hand, which can be embedded into some wearable devices. Some of the previous work are too bulky, some of them are placed in a weird location, and the remaining ones are fixed and therefore cannot be used in the wild. In this paper, we will introduce backhand pose that estimates the real-time hand poses using image from back of the hand, which could be taken by a simple tiny camera. And this camera could be included into some wearable devices such as smartwatch. This video here shows the real-time result of the image preprocessing. First, you can see the hand masking. We can tell that it is also robust to different lighting conditions. Next, these are the motion images of tapping different fingers. You can realize that different part of the back is changing when tapping different fingers. Okay, now we will introduce the DozoNet, a two-stream CNN network of which each stream uses a ResNet 18 as a backbone to extract the information from the hand images and the motion images. After that, the network is followed by an LSTM layer for temporal feature learning. To enhance the temporal feature learning, we use an LSTM-based common filter network instead of a normal LSTM. Finally, the network outputs a 19-dimensional finger representation, and it is recovered to 3D hand pose by an inverse kinematic-based hand simulator. Good, let's take a look at the real-time result of this work.
This area that I'm particularly excited about for future work.
To show the effect of our system, we performed several evaluations on 5 different users. The ground truth data is taken from a leap motion camera, and the right table shows the average angle error of doing 15 different gestures, comparing with other baselines. Where our method with Kalman filter outperforms all the other methods, both in the individual and the general model. Well, in order to show the robustness of the network, we also run the test in 5 different lighting conditions. The accuracy becomes worse in darker condition, but it was within 1 degree error comparing to the best condition. To note that our system even works under strong sunlight condition, where the IR-based leap motion camera cannot. Besides specific gestures, we also evaluate our system on grasp recognition. The right figure shows the confusion matrix of 50 tests for each grasp. In classifying 11 grasp types, our system achieves a 75% overall accuracy, while the worst cases appears in T1F, T2F, and T3F, which is the picking motion of the thumb with another finger. Finally, to show the usability as well as the potential of this research, we developed several types of applications. That's all for today's presentation. Thank you. Please feel free to contact me with any question, and you can also read our paper for a more detailed explanation.
Very good. So I think there was 2 pieces in that last video that I just wanted to highlight that I think is interesting and exciting for future research. One is the ability to have imaginary objects that suddenly mimic real objects. So we all have used a computer mouse. We've all seen a computer mouse. We're all used to using a computer mouse. And in that study, you actually saw that there were cases where it was just you didn't actually have that type of input device. You were just imagining you had that type of input device. And as you were moving your hand around with it, you were actually getting 1, 2, 3 button device and an actual mouse, even though there was actually no mouse in your hand. That's one branch that I think is actually quite interesting. This idea to, have imaginary objects that you're used to using, and the system is accurate enough to recognize your interaction with that imaginary object. The other one is actually recognizing the objects that you're actually interacting with. So recognizing that you're picking up a mug, you're picking up various objects. Because if you go back to the very original picture that I showed you at the very start, all of that work around human object interaction is all predicated on this. There's a camera watching you. But how is that going to be? Like, are we going to refit all of the homes? Are we going to refit all the physical environments? Is that actually the approach? So what I'm advocating for here is to repurpose the existing set of devices that we actually have on and around us, to actually use those to try to sniff out, to understand what are we actually interacting with. And then once we actually begin to understand those objects around us can actually become points for future interaction. And as promised, Becky, that's 45 minutes on the spot. I thought I was going to get killed for having so many slides and being over time. Sorry if I rushed through some of those, but I'm very happy to put out the papers if people want to have a look at any of those papers in more detail or answer questions now, of course.
Thanks so much, Aaron. That's a super interesting and cool series of projects. Very exciting to hear. Thanks again. Do we have any questions from our
or suggestions
audience?
On future work?
Suggestions, comments. Right, Oliver?
Yeah, I suppose one of the key things that stands out, and I just got the Ray-Bans, the Facebook Ray-Bans the other day, is obviously a lot of concern around the fact that there is a camera built into them and the whole privacy angle, right? So if you're using radar, that obviously takes away, or it makes it more acceptable that people aren't being directly observed. Or was any comments around that?
Yeah, for sure. I mean, I'm actually teaching a user interface construction and design course, which follows on from the HCI course that Nadine here taught last semester. And it's actually one of the very first case studies that we actually show. We talk about the Google Glass, and actually on Monday I'll be talking about the Facebook glasses. And the interesting discussion I've seen at the moment about the slow release of things like the Facebook glasses and the Snap glasses and the other ones is to kind of normalize the idea that you're going to have cameras in your face 24/7. And is that one of the strategies that companies are starting to take? That people will just, at the beginning it was all glass holes, then by the time everyone starts wearing them all the time, kids have them on the beach, kids are wearing them when they're out, doing their TikTok recording and videos. They just normalize it. And is that what they're trying to do? Are they trying to normalize that type of presence? But I have a feeling there's going to be a huge backlash against it. I mean, as we had with the Google Glass, there's going to be a big backlash, because I don't think people want to be recorded, especially in their social interactions with others. That's my feeling at the moment. But I'm interested. The students can actually pick that as one of their topics to build their group project around. So I'll be interested to see what the students come up with. Thanks, Oliver.
We have Abdo.
Yep. Thank you.
Okay.
Yeah. Well, first, thank you for the nice talk, and thank you again. Some of the works you presented was actually inspired me while doing my PhD in UNSW, and the reason that I switched to millimeter wave in last project in the PhD.
Cool.
So my question about the last piece of work, it's a very cool piece of research. Do you think that radar can be used as well in this? Because in radar you can be very sensitive as well. I used it for vital sign monitoring, among other things, and you can have multiple measurements that describe the same kind of motion that you're getting from the camera. So is there a value if we can test the radar in this kind of application? Thank you.
Absolutely. So it's interesting. We got into it. I mean, in a weird way, going in through the Google alpha program, that we got involved in the radar. But once you actually step into the radar community, you actually discover that radar has been used, as you can see, for like military applications, for weather applications, for ground penetrating radar applications. And when you actually start going to a lot of these radar conferences, you actually start to see, people are using radar for, cars for a long time. Radar is a very common type of sensor that's actually built in. So much so that Infineon, the people who make the original sensor that Google was using, their prime motivation for doing a lot of this type of radar work originally was just for distance-based proximity detection. And one of the big application areas that they were all looking at was basically trying to do presence detection for smoke alarms and for falls detection in care environments using radar. That was the big push. That's what they were all trying to do when we went to some of these kind of commercial products. So, but they were still looking at radar at a kind of a room scale. But I definitely think radar at the close proximity scale for actually doing that type of object interaction and detection is a very underexplored area. So yeah, definitely it's a big topic, I think. But we should also recognize that people have looked at it for measuring distance between cars and objects. So once you step into the kind of radar area, there's quite a lot of other research to draw on. It's not just in the sort of HCI field.
Yep, I agree with you. Thanks.
Thanks, Abdul. Is it Rohan next?
Yes, Rohan.
Hi, thanks a million, Aaron, for a fantastic talk. That was really great. I just had a question about the last. I mean, I've done a lot of work with doing kind of gesture systems for AR and kind of immersive systems, and you always have this problem of kind of the stiffness of the system just is never there when you compare it to a controller. And as well, using other types of cameras or using other types of sensors, do you think you'll be able to kind of bridge that gap where you're getting the kind of responsiveness that you actually need to kind of deploy these things where people will kind of feel really comfortable using them?
Yeah, it's a good question. I think it's that kind of engineering gap that we often leave when we're doing our research for doing our publications. It's probably why some of the radar projects that we tried to do with industry ended up failing, because they were getting up to like 99.5% accuracy, and that's just not good enough for being deployed into 100,000 commercial tills across Germany, for example. So I think we as researchers, we reach a certain limit of what's acceptable to prove the concept, but then to actually make that next engineering leap, it takes a lot more work, which is, I think, why we're seeing what's happening with Google. Google originally, they wanted the SOLI in the phone. They put the SOLI in the phone basically so they had something to counter the face detection that Google had. It only survived maybe 1 or 2 instances of being in a Pixel, and then it got dumped because it wasn't offering enough value, and actually it just didn't have a high enough reliability to be used as that type of sensor. But what we are now seeing is where it's being used for the Nest, and where it's being used for the at-home sensor, there it is actually working because the engineering is really honed down on a very few simple small gestures that work very, very reliably and just don't fail. And I think it's that big engineering hurdle that you have to kind of overcome to get it widely deployed. I don't necessarily think that's something universities do particularly well in my experience.
Sure. No, it's still an amazing system. I think it's a step in the right direction. It's just unclunky. Anyway, thanks a million. Cheers.
No worries. Thanks, Rowan. Tim?
Yeah, hi, thanks for the talk. So I'm just wondering, this is more on the technical side. So I'm wondering how precise, especially on the directional wise for the radar, and is it possible to register the object recognized on the radar with the object recognized from a camera?
Can you, okay. So yeah, that's the one big thing I learned with looking at radar is often our mental models around object recognition is built around the kind of computer vision world where you think there's an image, there's some data set coming in, and then there's an image to be processed. And then once I have the image to be processed, I can basically break it down. When you look at radar energy, the return characteristic is the way to look at it and to think of it. The best picture are those channels that you saw. Mm-hmm. So those channels are all you're actually getting. To make a deduction between that and the scene, you have to basically put in all kinds of other layers of modeling and framing to actually say, okay, well, this is the radar characteristics that I've got. I want to say, does this give me an indication that there's a car to the left and there's a banana to the right? You don't get that with radar. Like, you have to actually add in all those extra layers to basically build that bridging. But yeah, definitely something that was actually a fusion of unfocused cameras plus radar, I think could be quite interesting, or infrared plus radars plus computer vision. So I think hybrid approaches in the future would be definitely would be a good way to go. But I have to say, even my own mental model around radar is you often think of it in terms of computer vision, and that's not necessarily a very helpful way to think about radar, because you don't get back that type of return signal. You just get this very messy set of energy profiles, basically.
May I put a small comment here?
Sure.
Yeah, I think Aaron's talking mostly about the SOLI, but perhaps might be the newer models are increasingly employing this kind of mapping. So you have, for example, range azimuth measurement, where you at least get the difference between the angle of the objects reflecting the signal. So it tells you this is to the left and the right. But of course, it's bigger a bit than the SOLI model, but they are on the way to getting more and more compact, and they are using it in automotive driving for this purposes. So might be the future, or something about the future.
That's right, Abdul. And the other thing I would say that I didn't mention is that, and the SOLI can do this, but actually newer radars can also do this as well. There's a lot of beam forming technologies inside of radar. So you can actually sweep a beam quite rapidly through a scene. And then actually the signal characteristics you're getting back, okay, the energy is being directed in a particular region. Therefore, the other regions are less likely to be contributing reflected energy to the characteristic. And then suddenly, as you sweep the beam around the scene, then suddenly you're actually getting into the view of, well, now maybe I can actually match it up with the computer image that I've actually got. So yeah, I think what Abdo said about the new forms of radar, but also the beam forming characteristics you have with radar, all of these are new avenues.
So are they already available, or is still developing?
For myself, I use TI millimeter wave, and you can have this kind of measurements from it.
Any other questions or comments? I have one, maybe more like a speculative comment, Aaron. So with the objects around us, I think, I guess you are focusing on the ones they are like dumb, right? We are not really looking at IoT stuff where these objects can actually perhaps broadcast, what they are, what they do. So, but there is a tendency to go towards, this, future everyday things where, they become more activated, let's say. How do you see, these two different worlds come together, or kind of the tension between those?
It's interesting. I see Bob Kummerfeld on the line. So myself and Bob worked together like 20 years ago or something in the University of Sydney. And even then we were having discussions around types of, basically pre-IoT types of smart devices. So yeah, I think for researchers, it's a very interesting landscape to look at, combining passive objects with active objects that can actually do some sensing on their own, objects that can do no sensing on their own, and then combining the two together. Of course, it all grinds to a halt once you actually leave the wonderful world of speculative, research and design and academia, and you actually get into the wonderful world of industrial applications where it actually has to work reliably and predictably and safely. And I think we're still a huge way from that. I mean, a lot of these things, like the imaginary object, for example, like as you saw there, like the imaginary mouse. Imagine going and telling, your future family members, like, no, you don't have to buy a new mouse. Just imagine a mouse. Like, what does that mean? Like, just imagine a mouse, and then just wear this watch, and this watch will actually start, filling in the gaps for you. Like, and don't worry about having a phone in the house. Just imagine a phone. And it's that idea. I mean, it's a great concept. It would make some like awesome sci-fi movies. But I think the gap of having some smart objects that actually have electronics in them, as well as some, things that are passive, that is probably going to be the future. But then this kind of middle ground between the purely hypothetical objects and the physical objects, there's an interesting middle ground there where we can start to say, well, you don't physically have it with you, but the system realizes you're trying to act as if you did have it with you. Like making a phone call. Like if you could just do this, and then the system recognizes, like, oh, you're trying to make a phone call. And then something that was in your proximity, it doesn't have to be on a smartwatch, it's something in the proximity goes, oh, hello, I'm here to help you. And that's literally back to a paper myself and Bob worked on when I was just a postdoc working for him many years ago, where we had that type of scenario of like kind of smart objects, that any smart object in the environment would just like be available to you and it would just pop up and become something that you could actually use. So yeah, I think we're gonna have kind of a hybrid future in the future. But for researchers, it's a very exciting space to explore all these types of object interactions and smart object interactions.
Absolutely. Thanks, Aaron. Any final comments, remarks before we conclude?
Anyone who wants to work on radar and is looking for a part-time job, let me know. I'm hiring.
If I can ask a quick question. So on the computer vision side, many of my colleagues in Adelaide, so now they are using the camera to, based on image alone, to try to infer some biosignals or some states of the human. Is that also happening in radar? Is that someone?
Oh, for sure. Yeah. So actually, one of my colleagues back in Scotland set up a company called Biomedics, and it was using cameras to actually basically doing pulse oximetry, using kind of Kinect type cameras to actually recognize what people's pulse rates were. But yeah, the radar, definitely the health applications are big for it, especially for detecting breathing patterns. So anything to do with like aphasia, anything to do with sort of like nighttime breathing issues, people are using it for that. There's a group in Canada that actually look at it for detecting glucose levels inside of blood, but obviously it has to be in quite close proximity. And I've seen one group that's been using it to try to think about facial, not tumors, but facial, not aberration, something basically that was wrong with your face, and they were trying to use the radar for detecting that. I'm not so up to date on all the medical uses of radar, I would have to say, but it's definitely I know of a few that people are using it for.
Right. Amazing.
Thank you, Aaron, again.
Thank you, Becky. Thank you for hosting me. Thank you all.
Thanks for all the audience, and see you in our next talk next month by Judy Kay. And yeah, enjoy your weekend, and bye, everyone.
Thank you all. Bye-bye.
Bye.
Thanks, Aaron.
Thanks for organizing it, Becky.
Thanks for agreeing to